Welcome back to Circular Motion. Having just discussed and analyzed horizontal circular motion, we are ready to transition into vertical circular motion. Now, the next statement, the next sentence, will apply to any kind of circular motion, but I'm going to be applying it to vertical particularly. Namely, when any creature, animal, object of any sort moves in a vertical circle at a constant speed, such as a Ferris wheel, constant speed type of vertical circle, that object or creature needs a net, unbalanced, inward centripetal force, which always points where? Toward the center of the circle. Yes, that is redundant. Now, many vertical circular motions are not constant. They will vary in speed, but it doesn't matter. In that case, the centripetal force always points toward the center still, by definition, right? But will vary in magnitude, while a tangential force acts to change the speed. So something must be changing the speed, either slowing it down or speeding it up. So an example of that happening would be the side of a loop, like on a amusement park ride like Great America. So here is a train with students in the train, and here's the loop, the side of it. So let's say they're going down right now. Doesn't really matter. And at the moment, whoa, okay. Gust of wind about took the door off the house here. Is it okay?
Yes.
All right.
Sorry.
So right here we're at the horizontal side, and gravity is acting on it. mg pointing straight down. And then we have a track force, which is inward. Okay, in other words, the track is shoving inward on the car, on the train. That is what's providing the inward force. So let's go ahead and add the vectors and see what we get. We get weight plus track force. And we add those together, we get the total force acting on the object. So there it is. The part that we're really interested in here is the centripetal force, which is all provided by the track. Gravity does nothing to provide that because it's acting perpendicular. So what I'm going to call the support force is inward. Okay, gravity is down, and Fc is inward as well. So let's write the magnitude equation for this, which is simply as follows. Fc, the size of Fc. Oh, it's F track, and that is mv squared over r, an equation for the centripetal force. Okay, the vector addition will give you the direction of the force and the acceleration. So in this case, the train is speeding up. As you can see, the net force is more than just the centripetal force. The additional force that's acting is causing the train to speed up. So let's look at the acceleration now. There's the acceleration, always in the direction of the net force. We have the tangential acceleration provided by gravity, and we have the radial acceleration or centripetal acceleration provided by the track force. And we get our centripetal acceleration. Okay, so Fc, centripetal force, at the horizontal sides provided by the track, and that's it, since gravity does not act horizontally in this particular position. So at the sides, gravity provides the tangential force to either speed up or slowing down the object. And that is the physics of the horizontal side. And now we're going to migrate to other positions in the vertical circle. When we consider all the forces on an object in vertical circular motion, at the top and bottom of that motion, we find that it's the vector sum, the centripetal force is the vector sum of all real real forces acting on the creature. And there's usually two, and they are gravity. So gravity is mg, and support force. That force that's supporting the object. More commentary on that subsequently. So examples, we have strings, cables, chains, ropes, wires, worms, track, seat force, that's very typical. And other things like, frog tongue, fly feet, that provides a support force. Cockroach antenna, mosquito proboscis. Don't forget the moose dewlap. All right. All those things can be bona fide objects providing support force for the object. Now, let's consider what's going on at the bottom. The bottom will be the same in all situations. The physics of what's going on at the bottom. The top will take a little more finessing, so to speak. But at the bottom, for any vertical circular motion, puppy, relax. The support force has two jobs. What does the support force have to do? Consider for a moment my stopper of physics when I twirl it around, and let's consider at the bottom here. You can visualize it just hanging, the stopper hanging off of the string. What job does the string have? Well, it has to support the weight. If you just hold it there, the tension is equal to the weight. So it has to cancel out gravity, basically, acting on the object away from the center of the circle, right? So here's the circle, here's the thing hanging down, the object here, and gravity acts downward, which is away from the center. But then it's got another job. As this thing is twirling around, at the bottom, not only does it have to overcome gravity, but it has to supply the centripetal or inward force. So it provides all the centripetal force to enable the object to go in the circle. So at the bottom of any vertical circular motion, how does the upward support force compare with gravity acting down? Keeping in mind that this upward force has two jobs, canceling out gravity and providing the centripetal force. So if you're tracking with what I'm saying, you'll recognize right away that the support force, of course, has to be greater. So greater than gravity. The magnitude difference between those, between the support force and gravity, if you subtract those magnitudes, well, support force was already providing this, so they cancel. And what's left is centripetal force. That's the part 2 of this requirement for the support force. Okay, now let me show you that rather explicitly with a train at the bottom and a sheep landing on top to go along for the ride. That ram has got just as much right to ride in the train as the people do. Okay, so we have gravity acting down, so there's a vector, and support force. You could think of this as the normal force. That's the particular support force right now. Let's add the vectors. So here we go. mg, tail to tip, support force. Now the result of those, you start at the beginning and end at the end. So there it is. And that is the centripetal force. Do you see how the support force had to cancel out gravity and then provide the centripetal force? It all makes sense when you think about it. Well, so I want to emphasize here the importance of what we call the magnitude equations. So it's going to keep track of what the values of the forces are. The picture will keep track of directions. Don't try and solve these problems with keeping plus and minuses straight with the vectors in your head. You'll get confused. So let me show you what I mean. So FC, what is FC? There's a magnitude equation. FC, we start with the force. See, this is the net force. And so the real forces are Fs and mg. So we start with the force that's in the direction of the net force. In other words, the force that wins, and that's Fs. And in the opposite direction is mg, so we subtract it off. So as magnitudes, that's what Fc is. So that's really useful. So then it's mv squared over r. So knowing this, we have an equation for Fc. We know it's support force minus mg. We can easily solve for the support force in a typical situation. Or if you know the support force, you can solve for the variable in question. So the size of centripetal force then can be determined by this, or the support force itself, or anything else. All right. And now we will investigate as well what's going on at the top of the circle. Before, however, we get to vertical circular motion, let me show you a picture of the Moose Dewlap, since we brought that into the slide. So there it is. You know you want to grab that and put tension on it. And now we also have the mosquito and the proboscis entering into the skin, drawing blood, and you know you want to whack that thing. Looking at this mosquito in a little more detail, that looks like something from a science fiction show or some monster creature flick of some sort. Pretty cool, huh? And even at a higher magnification, look at that mosquito proboscis. Yes, isn't that an amazing thing? And here's some greater detail. This thing's sticking into your little capillaries. And you will notice that this proboscis with electron microscopy is very well designed to insert right into that capillary and draw that blood through. It's an amazing instrument. This is at a scale of 100 micrometers across here, I guess from here to here. So we're talking really small. That thing is like a fine-tuned instrument to slip into your skin and draw out that blood. So there you go. That's the mosquito. And let's not get in the habit of using this particular structure as the support force for a given problem in physics.